Good morning, everyone. And then let me know if you're not able to hear me properly. So today I'll be talking about the HoloScan-3D, which is basically a new term that we coined out of scanning near-field ultrasound holography. Okay. So I will talk more about this new technology that we developed many years back at Northwestern. And then we recently, in the last 2-3 years, we are putting more efforts uh, to do it in a better way. And then to get a high resolution, more depth resolutions and all those things. And then obviously I will go back to the olden days, which is my favorite, that, this is the first atomic force microscope or scanning tunneling microscope looks like, which is basically a handmade system that was designed in IBM Zurich back in 1986. You can see here they just uses parts and pieces and assemble them together into a dedicated scanning tunneling microscope where you have a probe and then you have a sample stage. So there it uses a conducting probe. Then you can see it's a little magnified view of that. And then they use the earlier to validate the basically that if you can get atomic resolution with this type of techniques, then they use the Scotch tape and then the peel of the graphene layer, and then they saw that hexagonal lattice structure that is seen typically in the graphene, and then that proves that this type of probe sample interaction, uh, where you apply the electrical bias, they can give you down to atomic resolution. And then you can see a little refined thing where you can see the setup here back in 1980s. And then this one setup is right now in the London Science Museum. It is available there. If you go there, you can see it there. So it's a pretty, and then that led to a whole set of new technology development in the arena of scanning probe microscope. Okay. And then this slide shows basically a comparison between the different techniques, TMs and STM, AFM, SEM, and so on. And some is a near field optical microscopes and acoustics. And then I will talk about the scanning or the ultrasound holography or hologram 3D, which comes under the category of acoustics microscopy. But you can see there, how we can differentiate them, whether they can do a restrictive analysis or non-destructive subsurface or just a surface. And then the other complexity in this electron microscopy technique is basically a very complex sample prep. So that is not required at all in the case of acoustics microscopes. On the right side, you can see the three techniques I mostly speak about. The normal AFM, I touch base with it. So I just give you a little introduction. And there's the ultrasonic force microscope, that we developed back in 2002. So that's basically exciting one of the sample or probe oscillations, and you can generate the extra mechanical force on the probe to measure the mechanical properties. And then the 3D hologram, which is basically a scanning near field ultrasound holography, where we can launch acoustics waves from both sample and the probe, where probe is a reference, and you can create a 3D hologram. Okay, so I will talk about that. In the case of atomic force microscope, as you know, is basically we use a silicon cantilever. It can be different types of cantilevers, and then we use the optical detection method. That means we align the laser on a cantilever and measure the deflection of a probe as it interacts with the sample surface. So there can be attraction or repulsive forces between the tip and the sample. And then based on that, we can generate the surface topography. And then the interaction between probe and sample is linear, and it's a constant force across the surface. And then you can see in the case of atomic force microscope, there are three different categories. One is the contact mode, where the probe is in physical contact with the surface. And you can get a pretty high resolution here, but you need a pretty soft probe. Then a non-contact mode, mostly useful for biological samples, where you don't need a pretty high resolution, is based on van der Waals interaction between the probe and the sample. And then the most popular mode is the tapping mode, where you oscillate the probe into resonance. And when the oscillating probe interacts with the sample, you can measure the height, the phase, and the amplitude change. And then you can measure some of the viscoelastic properties. And most of the advanced AFM techniques or functional techniques, they use this tapping mode concept as a base platform. And then you can end up doing chemical mapping or electrical measurements and all those things. Obviously, that use the different types of modules and settings, but at least the tapping mode is the basic. Okay, so then moving forward, I will mostly focus on acoustics microscopy. So back in 90s, the team in Oxford, they developed the ultrasound, this acoustics microscopy, where they use the transducers, and then there's a coupling fluid, which is the water, and then that through that water coupling fluid, they launch those acoustics waves and try to measure subsurface defects or voids and all those things. Obviously, based on the impedance mismatch between the different parts of the samples where the waves get scattered back. So obviously, there is a lot of signal loss here because of the coupling fluid, which is proportional to almost the square of the frequency. So you have a lot of loss here. So you can lose the signal intensity. It's also resolution limited, few microns. So basically, if you want to see nano scale features and all those things, it's not easy to see it. But at least, this was the origin of these acoustics microscopy. On the right, ultrasound holography, which is basically, you use a reference wave and object waves, and then through their interference, when they hit the object, you create a hologram or holography images. Okay. Again, resolution limited. And then at the bottom left is basically, the bottom right is force modulation microscopy, and that's where the AFM or atomic force microscopes come into the picture, where the probe is in physical contact. And then when the probe is in physical contact, then you apply some extra oscillation to the probe. And then the whole idea is that you can indent the surface with the AFM probe to measure the mechanical property. Okay. Again, it's pretty limited to the surface, and it's pretty limited to softer materials. Then on the bottom left is ultrasound, this ultrasonic force microscope. Then I will touch base more with about it, where basically we oscillate the sample at pretty high frequency. Okay, so we use piezo crystals and launch acoustics waves through those piezo crystals. And then the probe comes in contact, it generates the significant amount of force between the probe and the sample. So the probe sample interaction, if you see the next slide on the left, the force with the indentation is basically it creates a non-linear curve. Okay, a typical AFM force distance curves are almost linear, but here's extra non-linearity is coming because of the super resonant ultrasonic vibrations, where the frequencies of oscillations are pretty high than the cantilever resonance. And it generates the extra force on the sample surface. So you can extract the surface mechanical properties, but you can also go to some extent subsurface down to 50 to 100 nanometer below the surface. And then this opens up a new application back in 10 to 20 or almost 2 decades back. And then you can measure a lot of mechanical properties. Here in the schematic shows, launch of these ultrasonic force because of those acoustics or ultrasonic vibrations. Basically, you are generating some extra ultrasonic force, and that is very effective in the mechanical signals. And that depends, on the stiffness of the sample of subsurface features. So basically, that ultrasonic force allows the probe to indent much harder on the surface without deforming the probe, and you can extract the mechanical properties. And this is an example that we published in 2000. So you can see metal polymer trench structures. On the top left, you can see the atomic force microscope image. Then you can see those alternate aluminum and polymer trenches. And in the case of ultrasonic force microscope, you can see these dark lines in the topography. They just flipped back to the bright color contrast in the ultrasonic because they are aluminum. They have much higher stiffness than polymer. So you can see their mechanical contrast is much higher than polymer. So they appear as a bright contrast. And then you can also see a lot of these holes and voids that comes because of the polishing effects. So the whole idea is there. You can now have a high quality mechanical contrast. So you can study the different effects of polishing or chemical etchings on these interconnect test structures. Then comes the ultrasound holography. We developed that, the first version of that in 2005, where instead of launching acoustic waves from the sample, you can also launch acoustic waves from the probe. And then the probe can be a pretty soft or a silicon-based probe. Means we use this as a reference. Remember, in the ultrasonic holography, we use one as a reference, another as the one that is coming from the object. So we assume that always the sample, when we launch the acoustic waves to the sample, there may be cracks, voids, and all those things. So that can change the phase of those acoustic waves reaching at the surface of a sample. And then with these two acoustics wave that launch from cantilevers in the sample, you can create some beats, okay? And then the magnitude of those beat frequencies and the phase can change based on the defects or cracks or delaminations that is within the surface. And then we use the AFM probe as an acoustic antenna to monitor those subsurface contrasts coming from deep inside the surface. Okay, so it's a non-destructive. This is a depth sensitive. You can tailor the frequency to go little higher depth and also the resolution. It has excellent lateral resolution because we use pretty sharp probe. So your surface resolution is mechanical resolution down to a few nanometers. And it's very sensitive to change in the phase perturbations. Okay, because ultrasound is all based on the sound velocity, okay, and the velocity of sound changes if it goes from the different region of a sample based on the different density variation or this hollow void and all those things. So if you look at the mathematical formulations, it's just like a heterodyne detection type platform, but still uses a non-linear interaction between the different samples. So in the middle equation shows how we launch the acoustics waves through the sample and through the probe, and then we mix it at the interface. So the effective tip deflection or average tip deflection, it all depends, is proportional to the phase difference. Okay, and that phase difference basically gives the information about the subsurface imaging. Other terms are in the middle. W tape minus WS is basically the beats. Okay, and then we use those cantilever to measure those beat signals and identify the phase difference. So this is basically the theoretical concept, how we can do a heterodyne type detection. And then how the contrast. So what is the mechanism of the contrast we are getting out of this ultrasound? So it's basically, each material has a different acoustic impedance, okay? That depends on the density and the material and also the speed of the sound. So when the ultrasound passes through the boundaries, then, part of the wave is reflected, part is transmitted. So you create the phase and then the amplitude variation. at the surface, so the AFM probe can detect it. Okay. And then there can be regions of different stiffness, modulus density variations, and that can alter the propagation of ultrasound. And then the tip, which is pretty much sensitive to those beat frequency oscillations. We try to keep beat frequencies within the detectable range of a cantilever, because you cannot use beats megahertz, because then the AFM probe may not able to detect it. It's pretty hard to figure out, which type of harmonics you have to go and detect those things. So we try to use those beats within the cantilever detection. Okay. And then based on local phase variation and amplitude, you can get a mechanical contrast. So whatever defects, so the interference between direct scattered waves, you create a holographic patterns. So the amplitude contrast we can get here, that basically depends, what is the intensity of the signal, and then the phase contrast related to, the depth in the material thickness. Basically, we can easily identify if we have a standard samples, we can create a library and we can calculate the phase delays from each type of materials. And through those reference libraries, we can easily determine, at what depth the signal is coming by knowing the phase value. So not as straightforward, but I think that's pretty easy to do if we can have a good library. Then I will touch base with different examples here. We did in back many years back where we have an extreme ultraviolet lithography mask test structure that we get from Intel. And then they use these masks for a deep ultraviolet lithography based techniques. And in those techniques, they want, and those are very costly masks. So they want to analyze those things or defects or point defects without doing any cross sections and all those things, because each mask costs, it's pretty costly. So if you see on the left side, typical topography structures, when you get a holography image, then you also get a topographical. Then we use the specific acoustic transducers that can generate around a couple of megahertz oscillations. And then you can still see the same bump that has appeared on the topography. So this is not considered like a subsurface, but still a mechanical contrast from the topographic variation. But because these defects, these are created defects, because they want to see that if we create a defect at such depth, can we see it? And then when we increase the frequency, so if you increase the ultrasonic frequencies, what happens? The penetration depth increases. Okay. You loses the signal intensity, but there are ways you can increase those signal intensity. And then increasing the frequency also improve your resolution, because if you increase the frequency, your wavelength decreases. Okay. So when we increase the frequency, then you can see those features which are not appearing at 2 megahertz, they're appearing at 30 megahertz, those isolated defects. So you can see here, basically by tuning the frequency, we can go a little deeper inside the surface and see those defects. So this is one of the very good example, especially in this semiconductor. And then we also try to do a different approach that, why don't we create some artificial structures to fib few nanometers or few microns below the surface, and then let's scan with the holography, and then you can see the example here. The left is AFM, right side in the holography. You can see those trenches at the different frequencies. And when you are off resonance, or when you are at a different frequencies, other frequencies, this technique is called the scanning near field thickness resonance, where we use a special piezo's to excite to resonate the sample rather than the piezo. So in that case, you can get a pretty high contrast. So you can see a subsurface contrast, but at the same time, when you're off resonance, they're not seeing the contrast. So this is another example that proves that, this is indeed a subsurface sensitive technique, and you can see these things. There's another example here where you can see bottom left is basically a typical AFM image, holography image. And then in the holography image, you can see those defects on those trenches, which is not visible in the AFM image, which is simply shows the trench. So we saw that defect and then we correlated with FIB, focus ion beam cross section. And because we pointed that and then we used the FIB, we mill it, we did a cross section and then you can find a defect here. So that correlate 1-to-1 with the other technique also that, this is indeed a buried defect that we can see it through holography method. On the right, we can see the buried pattern. Okay, so you can basically image those contrasts coming from that. So this is a typical example of a live image where you can see sets of 4 images. So that on the left side, the top 2 are the topography, and the bottom 2 are left side is the amplitude holography, on the right is phase holography, where you can measure both amplitude and phase. And in this real time, you can see that some of the features which are not visible in topography, you can see those defects, cracks, delamination across the edges of these trenches. You can see them pretty clearly. So that demonstrates how useful this technique is, especially in the semiconductor industry, where you do the cross sections, all those in cross section SCMs or TMs. Rather than that, you can use these techniques to find those things. Now, recently, few years back, we moved this technique to biological arena where we just want to see that can we apply it to biological materials. So in that case, we took a magnetic nanoparticle, which is like a magnetic core, then is covered with silica core cell, and then antibodies on the top. So usually we use TMs to see these magnetic cores. And then on the top right, you can see a typical AFM topography where you can see individual silica-coated magnetic particles. On the bottom left is typical tapping mode image. Tapping mode means you just oscillate the probe with resonance and interact with the sample, you create a phase and amplitude image. So this is a typical phase image of a tapping, but on the bottom right, you can see ultrasound image where you can see the contrast coming from the different layers. The central one is basically the magnetic core. It is giving you high contrast because magnetic core has it's pretty stiff. So your contrast is pretty high. And across the ring is basically the silica cells. And on the top, you can see those antibody layers. So basically, you can identify all these 3 components with this holography technique rather than pursuing a complex TM measurements. And you can identify all of them. So this is one of the example. Then we also did a lot of these endothelial example lungs. These are the lung cells, and they are stimulated with thrombin and S7P as stimulating agents. So thrombin increases the stiffness of the cells across the nuclear region, and S1P is another stimulating agent that increases the mechanical response at the periphery regions. And the thrombin creates a lot of stress fibers, you will see here. But in the real time, this is a live image in the real time in liquid. You can see how the mechanics changes over a period of time in real time. So you can do these things. You see, example here, cell mechanics. You can see as the time pass on, the effect of thrombin is basically within the nuclear region. You can see the stiffness increases, and with the S1P, and with the addition of time, you can see periphery contrast increases. So this is how you can do a live cell nanomechanics, but you can also image some embedded nanoparticles within those cells through this technique. This is pretty unique because you cannot use SCM and TMs to see anything within the cells. For example, if you want to see nanoparticles, then how you can see it? So you can use the holography technique to identify the contrast coming from the nanoparticles. This is unique examples of left is a topography where you can see endothelial cells, and the right is when is thrombin treated. You can see thrombin creates some intracellular fibers. So it decreases the gap between two cells. So this is basically they use in lung injuries treatment where when the lung collapse, when the cells are collapsing, they use thrombin. So they can basically use stress fibers to connect those cells so they can revive the tissue. Okay, so this is, and you can see in the holography, all the stress fibers are showing up, which is not visible on the left side. So it's a pretty, and then also the contrast depends on the stiffness. So the brighter contrast is more stiffer as compared to duct. But you can see the resolution and also the revelation of these fibers. Then there's another example that you can image nanoparticles in the cells. Okay, so this is a typical example that shows these nanoparticles within the cells. And then you use the FM probe to see that. The figure C shows the topography, where you can see a typical topography of some section of the cell, but on the D figure D, that shows the same cell, but you can also see the contrast coming from those particles. Okay, so these are the red blood cells. And then this is a powerful technique to identify those type of particles. And this is pretty much in analogy, you can do like an ultrasound. It's just like an acoustic technique where you can see something inside your body, not at nanometer scale, but at least, few tenths of a microns. But this is pretty much comparable to that technology, but the resolution here is pretty good. So then the last part I will touch is basically we have a big program going on with the Toyota Motor Corporation, and then where they are coming with the battery electrodes. So they want to identify any subsurface defects, cracks, and delaminations within those battery electrodes deep inside the surface, from the surface to go and basically deep inside the sample. They don't want to do any cross sections, SCMs or TMs. They just want to use this technique to see it. And they also want to do some correlative study where, we can also do cross sections with the TM, not use the correlative, XPS or SIMS or FIB-based techniques to match what we get in the holography as a proof of concept. So you can see the left is typical topography structures, but on the right, you can see the defects, voids, cracks, and delaminations within that electrode structure. But the most important, what they want us to do, that can we do a 3D tomography type of imaging or a 3D reconstruction. So the beauty of this is you can see it here now. This is a slice X, Y, Z, but look at the Z scale. So as we go different depth, you can see this is a reconstructed image, layer by layer. You can see how the contrast of different layer changes or the mechanics changes, because when the mechanic of a stiffness changes across different layer, the contrast changes. So as you go from 1 micron to 10 micron below the surface, you can see how these mechanics changes. And this is a pretty unique way that we are doing. We are planning to do artificial intelligence-based reconstruction to just make sure that we are getting contrast from each layer and then reconstruct those images. This is pretty much at the early stage, but this is the way how we are moving forward with Toyota. So we can go 10 micron, 20 micron, 30 micron, 40 micron. This all depends, what type of frequencies we are using, so we can have a greater penetration depth. But as I said, higher the frequencies, then the signal will get weaker as you go deeper. Then we are finding the ways how we can amplify those signals so the frequency or the signal doesn't decay as you go deeper. And then when you go deeper, obviously you can go to the different layers and all those things. But this is pretty unique in that sense. And then we are also planning to use this ultrasonic probe for unlocking the skin secrets. We planning to work with the dermatology department here in Feinberg, so where we can see if we can use ultrasound to monitor the underlying structures of the skin, like dermis, epidermis, and you can do a real-time quantitative analysis of the skin layers. Uh, so you can basically assess the impact of any therapeutic interventions on the mechanical properties as well as in how the inflammation is progressing within the skin. So this way we can uniquely apply this type of technique. And then now we are doing with the Toyota, we can apply similar 3D reconstruction based imaging techniques. So you can go layer by layer, and try to find the nanomechanics, which is not possible at all to do with any other technique. Okay, so this is the last slide. And then I think I'm open to any questions. Thank you very much.